SwayamPrabha. Digital India. Educated India.
Hello everyone. So in the last class we were talking about the filtering operation involved in LES, and just to refresh your memory, if you look at this plot here shown on the slide, what we have is the instantaneous velocity, of course, which is the thin line on the top as marked here, and you apply a filter to it. What you get is U bar. Right? So that is the thick line on the top. That's a U bar. And as you can see, it is smoother than U. U bar is smoother than U. That's the idea of having a filter, so that you smooth out the velocity, you take away the high frequency components, you only let the low frequency or low wave number components go through, and that's what you have. So you have a smoother velocity profile. That's what the filtering does. Now, on the bottom of this plot, you will see there are again one thin line and one thick line. The thin line represents the residual velocity, so U prime, which is equal to U minus U bar, isn't it? Now, if you smooth that, if you make that go through a filter, if you filter that velocity, filter the residual field, okay? So the filtered residual field is the thick line on the bottom. And as you can see, the filtered residual field is not zero, as I have written here. It is not zero. So unlike what you had in the Reynolds decomposition, where you had U is equal to U minus U mean, isn't it? Here, the mean represents the time average. Now, if you apply a mean to both sides, you will get U mean minus mean of U mean. And mean of U mean, because you're taking an averaging in time, becomes mean itself, because the mean is unique. Here though, when you're doing a filtering, so just to continue, what would happen here is U mean minus U mean, which is equal to 0. So that is how you get the mean of the fluctuation, right? In Reynolds decomposition, the mean of the fluctuation being equal to 0. Whereas here, what is happening is your U, your instantaneous field, is obviously quote unquote random, because it is 3D and time dependent, and your U bar is also 3D and random. Okay, random in the sense that we have been talking about in this class, seemingly random, right? So that would make it random. That means U minus U bar, which is again another random variable, is your U prime, which is the residual field, and that cannot be 0, because U minus U bar, because U bar itself is not unique like you had U mean. So U minus U bar becomes U prime, which is the residual field, and that won't be equal to 0. So when you take a filtering over it, so that is why U prime bar is not equal to 0. So I hope that is clear. So in the last class, I had shown some examples of filter functions. And here we are going to look at filter functions in spectral space. So I'm going to go over to the next slide and describe what that is. So let's say you have a Fourier transform of the velocity. So you have U hat of kappa as shown here, which is basically the Fourier transform operator applied to the velocity field. So that is what is f of U of x. So that means this is how you define it. So if you have your Fourier transform of the velocity given by this, then the Fourier transform of the filtered velocity field, so that is U bar hat, and it is a function of the wave number, obviously it's in spectral space, would be defined as the Fourier transform of the filtered field. So the Fourier transform of U bar of x, which is equal to, look at this, you have the transfer function multiplied by the Fourier transform of the velocity, right? So this right here is the transfer function, which is basically the Fourier transform of the filter function. Now, if you remember, the filter function was defined as, okay, so the filtering operation in physical space was defined as integral g of r times u of r minus x. Let me just make sure it is, I believe it is g of r minus x. No, that is correct. So g of r times u of x minus r, right? So writing that here, u of x minus r, and that would be dr. G of r times u of x minus r, and that is your filtering operation. So as you can see, it is a convolution operation in physical space. If you take a Fourier transform of this expression that I have written here on both sides, then on the left hand side I will have the Fourier transform of the filtered field, which is what this is, u bar hat of wave number, u bar hat. And on the right hand side, if I take a Fourier transform, a convolution operation becomes a product operation in spectral space. This is a property of the Fourier transform. Any convolution operation in physical space, if you take a Fourier transform of it, becomes a product, a simple algebraic product in spectral space. That is what we are utilizing, and it is actually one of the advantages of using a Fourier transform, because a convolution operation is relatively more complicated than a regular algebraic product. So any convolution operation in physical space gets converted to an algebraic product, and that is what is happening here. So if I take the Fourier transform on both sides, I will have u bar hat of kappa is equal to the g hat of kappa, which is the transfer function, which is basically a Fourier transform of the filter function, multiplied by u hat of kappa, which is the Fourier transform of the velocity field itself. Okay, so g hat of kappa, as I've written here, is 2 pi times the Fourier transform of the filter. So I have g hat of kappa is minus infinity to infinity, g of r e to the minus ikr, e to the minus ikr, I kappa r dr. Okay, so that is 2 pi the Fourier transform of g of r. Okay, so that's what we have. So essentially the transfer function is the Fourier transform of the filter function. Now remember, since g of r is real and even, right? G of r is real and even, so is the transfer function. So that means because g of r dr or g of r satisfies the normalization condition, you have minus infinity to infinity, g of r dr would be equal to 1, and from here, if I just substitute kappa is equal to 0, I'll get integral minus infinity to infinity g of r dr, isn't it? In this equation, if I substitute kappa is equal to 0, I get this. Then I have integral minus infinity to infinity g of r dr, which is going to be equal to 1, and from here this would be equal to g hat of 0, which is equal to 1. Okay, so then because of the normalization condition, g hat of 0 is equal to 1. Now if you have something like a sharp spectral filter, and we saw those examples, so now let me go back and see what this plot means, right? So I have here the transfer function, just like previously I had the filter function shown for 3 different examples. I'm showing the transfer function for the same 3 examples, which are the box filter, the sharp spectral filter, and the Gaussian filter. Now if you remember from the table that I had shown earlier, look at this. The box filter is a Heaviside function in physical space, and it's a sinusoidal function in spectral space. The sharp spectral filter is a sinusoidal function in physical space and a Heaviside function in spectral space. So it got flipped. And you have the Gaussian function, which is exponential in both physical and spectral space. Okay. Now this was the filter functions in physical space. So as you can see, the dashed line here is the box filter. like a step function. That is the Heaviside function in physical space. The box filter is a Heaviside function in physical space. The Gaussian filter is like a regular exponential function, which is the solid line here. And the sharp spectral filter is like a sinusoidal function. As you can see, it's a sinusoidal function, which is the dashed dot line here. Now coming to the transfer function, the box filter, right? The box filter is a sinusoidal function. As you can see, it is going up and down on the right side as well. The sharp spectral filter is now a Heaviside function in spectral space. So that is why you see this step function here, the Heaviside function box filter. And then your Gaussian function is again the solid line here, which is, we know it's an exponential function. So it looks like an exponential function. So those are three examples for the transfer function as I have it, right? And what the sharp spectral filter does is it basically destroys all Fourier modes that are greater than the cutoff wave number kappa c. So kappa c is corresponding to your filter width. Remember, every filter is associated with a filter width. That filter width takes into consideration only motions or scales larger than that filter width. Everything inside that filter width or below that filter width is not considered, is modeled, right? So they are not resolved, they are not considered. So in the analogy to wave numbers, basically the sharp spectral filter will remove all components that are greater than your cutoff wave number kappa c, which is corresponding to the filter width delta. So kappa c is pi over delta, right? So earlier, if you remember, when we were talking about direct numerical simulation, we said kappa max, right, would be equal to pi over n max, or kappa would be equal to pi over n. In the case of DNS, we are not talking about max, we are talking about n being the largest represented wave number, kappa max being the largest represented wave number. So we would say kappa is equal to pi over n in homogeneous turbulence. So by the same token, we are saying the cutoff wave number corresponds to the filter width. So kappa c is pi over delta, right? So it would remove all the wave numbers greater than kappa c. Now here is an example. What I have shown here is a 1D spectrum. We are going to be discussing the filtered energy spectrum. What I have shown here is a 1D spectra E11 of kappa, which is like a longitudinal spectra in isotropic turbulence, and it is normalized with the kinetic energy and the integral length scale. So U squared average multiplied by L11. That's on the y-axis. On the x-axis, I have wave number, obviously normalized, so it's multiplied with the longitudinal integral length scale. The spectra, the solid line is the spectra that you would obtain from a model spectrum. Okay, so we have looked at the model spectrum at length before, and if I were to plot E11 of kappa, this is what I would get. So as you know, the lower wave numbers, we have the energy containing range, then you have the inertial subrange, then you have the dissipation range, isn't it? Now, what happens is that there is also a dashed line shown here, and that is your filtered spectrum. That is your filtered spectrum. There's a vertical line, dotted line shown here representing kappa is equal to kappa c. That means everything beyond kappa c is removed. Everything beyond kappa c is removed. Kappa c is corresponding to your filter width, pi over delta. So above kappa c, we are removing all those high frequency components. And as you can imagine, kappa c is in the inertial subrange, ISR as we used to call it. This is the dissipation range. This is the energy containing range, approximately. And kappa c is in your inertial subrange, and that is what you need it to be. You need your cutoff wave number to be in the inertial subrange. Remember, we are resolving all the large scales. So at the minimum, your filter width should go till the energy demarcation length scale. But again, these are not hard set numbers. So it's better to be below, slightly below the energy containing range for the demarcation length scale for the energy containing range, the LEI, if you remember. So it is better to be in the inertial subrange, and that is what is done here. So my kappa C, I choose it to be in the inertial subrange, and then when I look at the filtered energy spectrum, as you can see, it drops down quite quickly right after kappa C. Now, the sharp spectral filter removes, annihilates, destroys all wave numbers greater than kappa C. Here, the filtered energy spectrum is obtained using a Gaussian filter. So then you might ask the question, why is it not dropping down immediately? Why is this tail there? Right? You might ask the question, why is it tailing off? It takes a while to actually drop off, right? And in the process, you are ending up getting energy in these ranges. Why are we getting energy there? If it is destroying all the wave numbers after kappa C, why are we getting energy levels even at wave numbers between kappa C and whatever this wave number is? The answer to that question is because the filtering here is done using a Gaussian filter. The Gaussian filter does not cut it off immediately. If I go back to this, the transfer function shown here, this is the Gaussian filter, the solid line. And as you can see, there is some wave numbers that it is still considering beyond that kappa C, because this is your kappa C, kappa over kappa C equal to 1 here. Right? That is your kappa C wave number. So slightly beyond 1 also, there are some wave numbers being considered. And that is what you're seeing in the filtered energy spectrum. Okay? So the energy spectrum is shown and it is 1D. And the filtered energy spectrum is also shown using a Gaussian filter. The cutoff wave number is shown just to show where it would actually cut it off. But in the Gaussian filter, the cutoff wave number has something more to it. I mean, you will get some energy slightly beyond kappa C as well. Okay, so that is what is described here. So again, just to give a little bit more of a description, if you consider your U of x to be a statistically homogeneous field and consider the fluctuating field to be u minus u bar, then your autocovariance is u of r plus x plus r times u of x, mean of that's your autocovariance. The energy spectrum is basically the energy spectrum is basically the Fourier transform of the autocovariance. That is what we have done here. If you were to calculate an integral length scale, that is the integral of the autocovariance, obviously normalized with the kinetic energy as well. And your delta, if you choose it such that it is equal to this energy containing range demarcation length scale, which is about 1/6 L11, then you will be resolving about 92% of the energy. Okay, that is for 1D. In 3D, that would be about 80% of the energy because you are considering multiple velocities, multiple length scales, and you would have to take sort of an average of that, right? In a sense, an average of that. So that's what we are trying to say here. So now, if I want to talk about the resolution of the filtered fields, okay, I want to talk about now the resolution of the filter field. So here a little bit of strategy comes into play as to what is my velocity field going to look like and how many modes am I considering, as in how many wave numbers am I considering. We did the same thing for direct numerical simulation. So we took u of x to be a statistically homogeneous field. We have a box from 0 to L, and if you have a filtered field which is u bar represented by discrete values on n nodes of a uniform grid that has a spacing L over n. So your grid spacing is h, which is equal to L over n. We did the same thing for direct numerical simulation. Okay, except there we were talking about u being resolved exactly for all the length scales. So that means we did not have a u bar, we only had a u. Now here u bar is resolving on a grid that has a grid spacing of h equal to L by n. Now the question that you have to ask before moving forward is, what is the value of H? What adequate value of H is required so that you resolve U bar properly, adequately, accurately? Okay. So now again we are considering homogeneous turbulence. So let's say U of X is periodic with period L, and then you consider the Fourier series for U and U bar. Okay, because only then can you consider the Fourier series. Now the Fourier series for U of X is written as an inverse discrete Fourier transform. So U of X is summation Cn times I to the I kappa n x, where Cn is the Fourier mode corresponding to U of X, right? And this is obviously summed through n is equal to 1 minus half n max, and this is half n max. Now note that this is corresponding to DNS. Remember, U of X is if your grid was DNS. If you are doing a direct numerical simulation, then your box is big enough to resolve all the length scales, and the grid size is small enough to resolve even the smallest length scale, which is the Kolmogorov scale. So that is why the maximum number of grid points is n max. Okay, on a grid that is large enough to resolve the integral length scales and the grid size being small enough to resolve the Kolmogorov scale, your maximum number of grid points in each direction is n max. So you are summing over 1 minus half n max to half n max. Cn is this Fourier coefficient corresponding to the nth wave number, so that an nth wave number kappa n is 2 pi n over L. Okay, we have seen this in DNS, except we did not use n max because there we only had DNS. Here we have a filtered field coming up soon, so we are considering a situation where if you had DNS, if you were resolving all the length scales, then n max would be the maximum number of grid points. That is what you're considering. Now, this even integer n max, as I was saying earlier, determines the maximum resolved wave number. If you are resolving the smallest length scale, it is going to represent the maximum resolved wave number. So kappa max is equal to kappa corresponding to the n max over 2, isn't it? Because it is half and half, remember? So kappa max is pi n max over L, which is sufficiently large to resolve U of X. What does that mean? Resolving the Kolmogorov scale. So kappa max, according to the rule that we were using earlier, will be basically corresponding to 2 times the Kolmogorov scale. If you remember, it's about 2.1. We wanted it to be that ratio. So 2 times the Kolmogorov length scale would be corresponding to the maximum resolved wave number for DNS. And that is what this would represent. That's what kappa max would represent. Now, the discrete Fourier transform provides a one-to-one mapping between Fourier coefficients and the value of U of X on a uniform grid with n max nodes. That is, U of n h max, where n is equal to 0 to n max minus 1, where h max is the total box size L divided by n max, isn't it? If you were doing a DNS. That is basically pi over kappa max. So your H max is pi over kappa max. So this is the H max, which is the largest grid spacing that is sufficient to resolve U of X exactly, right? So when we say sufficient to resolve U of X exactly, that means resolving up to the Kolmogorov scale. So this is if everything was DNS. Now all of this changes when you apply LES. All of this changes when you apply LES. So the Fourier series of the filtered field is written as now an inverse Fourier transform, inverse discrete Fourier transform, which is U bar of X. And now what you're doing is you are writing it as summation again, but your Fourier mode is now a filtered Fourier mode. So Cn bar e to the I kappa n x, going from n1 minus half n max to half n max. And as you can imagine, Cn bar, the coefficients of U of X, attenuated by the transfer function of the filter. So that means Cn bar is this transfer function, whatever you use, sharp spectral filter, box filter, Gaussian filter, whatever filter you use, the transfer function multiplied by C of n. So that is how you get the Fourier mode, right? So now your filtered velocity field is known, except it is obtained by taking the transfer function and multiplying it by the Fourier mode of the fully resolved field u of x, not the filtered field. And the filtered Fourier mode is obtained by taking the transfer function multiplied by the Fourier coefficients correspond to the fully resolved field. So here what we have done is we have considered what if it is direct numerical simulation, right? And then you have n max number of grid points in each direction. Here for the purposes of discussion we are pretty much only considering 1D. And we have n max being the total number of points in one direction, and kappa max is the wave number corresponding to the total number of points. So then what we have is, you will have, if you write it as a discrete Fourier transform, then u of x is summation 1 minus half n max to half n max, isn't it? Cn e to the I kappa n x. So this is, if it was direct numerical simulation, you're fully resolving it. And that kappa n is basically the maximum resolved wave number for fully resolving x. So that would be 2 pi n over L. Now the same thing, if I were to calculate what is the maximum wave number, maximum resolved wave number, kappa max, would be kappa corresponding to n max over 2, right? Which is basically the maximum number of grid points, but the wave number is half of that, remember, because you're going from negative to positive, isn't it? So kappa max would be pi n max over L, which is obviously sufficiently large enough to fully resolve u of x. So that kappa max is the maximum resolved wave number, and the grid size corresponding to it is h max, which is basically L over n max, total box size divided by total number of grid points, if it was DNS. You apply the same concept now into LES, and then what you have is u bar equal to Cn bar times e to the I kappa n x, but Cn bar is basically the transfer function multiplied by Cn, because a filter has been applied. So now, depending on what filter we have here, we will see what Cn bar is, and that we will see in the next class. So that, and for the purposes of discussion, we'll be choosing a sharp spectral filter in order to discuss this further. So I hope this is clear. We will continue this in the next class. Thank you.